to talk about the theory of non-uniform velocity, which is a very important concept to understand in order to analyze vibrations that can occur in a drive shaft. This theory of non-uniform velocity states that in a single universal joint operating in an angle, the input yoke will travel at a constant speed while the output yoke will speed up and slow down twice each revolution. That concept is a little difficult for a lot of people to understand, so we've designed this little demonstrator to illustrate the principle, or the theory, if you will. We have here a short one-piece, two-joint drive shaft that's being powered by an electric motor. An electric motor, as you know, puts out a very smooth, constant flow of power. There are no cylinders firing, so its output will be turning at a constant rate of speed. We also have this short one-piece, two-joint drive shaft and an output yoke on it. There are three sprockets on this shaft. One of the sprockets, right here, is connected to the output shaft of the motor. So this sprocket is going to be reflecting exactly what this input yoke is doing. This sprocket is going to be reflecting exactly what this output yoke is doing and what this input yoke over here is doing. This sprocket, being connected to the output yoke, is going to be reflecting exactly what it's doing. We've got teeth on the sprocket that are going to make a noise when I hold this credit card up against it. Also, there are tape stripes on the sprockets that you will be able to see any changes in speed or variations in velocity. One of the things that I would like you to keep in mind while we're doing this demonstration is to relate what you see here to your passenger car or truck. Picture this, if you will. This being the engine, transmission, and clutch. This, of course, is the drive shaft. And back here is the rear axle in your vehicle. If you keep those mental images in mind, it'll be very easy for you to understand things about vibrations when we get into the angle portion of this demonstration. All right, first of all, just to show you that everything is on the up and up, I don't have anything up my sleeves, and this isn't a magic show. I'm going to power this motor up and show you what takes place on these sprockets with the shaft configured the way it is right now. As the shaft is sitting, right now I have absolutely no angle on this universal joint and absolutely no working angle on this universal joint. So, here's demonstrating the smooth, constant flow of power coming out of the motor. Now, you didn't hear any rising and falling of the pitch of that one. Now we're going through one universal joint, but it's not operating at an angle. Therefore, if the theory holds true, we should not hear any change in this sprocket, and there should not be any speeding up and slowing down in this yoke. Let's see if that's true. And I think you saw that there was no change or variation in the way this sprocket moved compared to this one. All right, now we have two universal joints in this drive shaft. Here's the one that in your vehicle would be going into the rear axle, and this sprocket is going to be reflecting what this output yoke is doing. But again, there's no working angle on this universal joint, so there should be no variation in pitch. Let's see what happens. And I think you saw that there was no change in pitch on that sprocket either. All right, now let's put an angle on this universal joint up here in front and see if we can make this change in velocity take place. Here again is the smooth, constant flow of power coming out of our power source and is reflecting what this input yoke is doing right here. No rising and falling in the pitch. All right, now let's see what this output yoke is doing. Remember, if the theory holds true, this output yoke should be speeding up and slowing down twice each revolution. Let's see what's happening on this sprocket. I think you can hear that rising and falling in pitch. All right, let's see if we can figure out what's happening here, or why is this taking place. I think the best way I can describe it is to mentally shrink yourself down to about this tall and stand right here on the ear of this input yoke. And as this input yoke turns, you, standing on the ear, will be turning also, and you will be going around in a circle. Now, as you're standing on this input yoke and looking at the output yoke, relative to you, the output yoke won't be traveling in a circle because it's at an angle to you. It will be traveling in an ellipse. Because whenever you take a circle and turn it on edge, like this, at some angle relative to you, now you have an ellipse. All right, so if the input yoke is traveling in a circle, and the output yoke is traveling in an ellipse, let's trace our way through one revolution and see if we can determine the speeding up and slowing down. My left hand will be the input yoke, and it's traveling at a constant rate of speed. My right hand will trace the path of the output yoke. Now don't forget, the input and output yoke are mechanically connected by bearings that can rotate. All right, here comes the input yoke traveling at a constant speed, and here's the output yoke. In order for the output to stay up with the input, it has to slow down, then it has to speed up. It has to slow down, and then speed up. That's what happens during one revolution when a single U-joint is operating at an angle. All right, now, if this shaft were in your vehicle, as it's sitting right now, we know that because of the non-uniform velocity that's been induced by this working angle on the front universal joint, this whole shaft is speeding up and slowing down twice each revolution. And as the shaft is spinning faster and faster, you now have what we call a torsional vibration, or twisting motion in the shaft. Through the second universal joint, since we haven't done anything to change what's happening up here at the front of the shaft, no working angle, now you've got this speeding up and slowing down being fed all the way through the back to your rear axle. This is going to be present as a vibration in your rear axle. It can destroy input seals, bearings, and even destroy ring and pinion sets. Now, the unique thing about this form of vibration is if it doesn't destroy anything in the rear axle, it's going to be reflected as a wave all the way back up through the front of the drive shaft, taking out this universal joint and its bearings, this universal joint and its bearings, and feeding on up into the clutch and transmission. Input splines will be pounded out. In the transmission, you're going to fail bearings, seals, and the weakest point of most mechanically shifted transmissions is a synchronizer. Mysterious synchronizer failures can most often be traced to a torsional vibration in the drive shaft due to angularity. Now the question comes, what can we do to correct this situation? Since we have induced this motion here in the front of the shaft by this universal joint, what we have to do is correct it at this universal joint back here. And the key to correcting it is to have a joint working angle on this universal joint exactly equal to the joint working angle on this universal joint. Well, not exactly equal. We'll allow you a tolerance of plus or minus 1 degree. For instance, if this universal joint has a working angle on it of, say, 5 degrees, we'll allow you a working angle down here anywhere from 4 to 6 degrees. So let's put an angle down here and see if we can correct this speeding up or slowing down or torsional vibration in the shaft. All right, we've got an angle down here that is within 1 degree of this angle right here. And now let's see what happens all the way through the shaft. Here again, the input yoke of the shaft coming from the power source. Just as it was before, no rising and falling in pitch. Now, we're going through one universal joint operating at an angle, so we're going to have the output yoke speeding up and slowing down. Now, by having this universal joint within 1 degree of this universal joint, as far as operating angles go, we should have corrected the torsional vibration down here on this sprocket and the output yoke of this universal joint. Let's see if we've done that. And I think you can see that there is now no change here. Well, let's trace through on the board again what we've done to make this change. This is the input yoke of this joint traveling in our circle. Here's the output yoke of the universal joint traveling in an ellipse. Now, by putting an angle equal down here, we have this yoke doing the same thing that this yoke was, which is traveling in an ellipse. And by having the angle equal, this universal joint compared to this one, this output yoke now should be traveling in a circle. And producing no torsional vibration here on the output. All right, we've got a pretty good handle now on non-uniform velocity as being caused by angles. But really, that's only half the story. The other half has to do with phasing, because a drive shaft that's out of phase can also produce non-uniform velocity and its associated vibrations. As you'll recall, a shaft that is in phase will have its inboard yoke gears lying in the same plane, and this shaft right now is in phase. However, let's turn it out of phase and see if we can produce some non-uniform velocity again. Now, as we had this shaft configured before we changed the phasing, the non-uniform velocity was corrected because of the equal angles. Well, now let's see what happens with this shaft turned out of phase. Here again, coming out of the motor and on this input yoke, should be traveling at a constant rate of speed. It is. Going through one angle, this output yoke should be speeding up and slowing down still. Now, we're going through an equal angle, but we've changed the phasing. Let's see what's happening on this output yoke right here. Sounds like we're back to our condition of non-uniform velocity. Now we've got that vibration traveling as a wave all through the vehicle. We'll destroy rear axle inputs and bearings, be reflected back up here, taking out the universal joints and everything in front of this. Clutch, shafts, the transmission bearings and seals and synchronizers. The question comes up now, why does turning this shaft out of phase cause what you just saw and heard happen? Let's go back to the board and see if we can figure some things out. If this is the front of the shaft and this is the rear of the shaft, when we were just talking about angles, we had the circles reflecting what some of the yokes were doing, and we had the ellipses reflecting what the output yokes were doing. But notice how the ellipse happened at the same time. Well, when we turn the shaft out of phase, what we have done is made the ellipse happen at a different time. Somewhat like this. Now, the circles and the ellipses don't cancel each other out. You've got speeding up and slowing down taking place at different times throughout the shaft. And again, producing non-uniform velocity and its associated vibrations. To sum up then, what we need to have on each drive shaft as it's installed in the vehicles are working angles exactly equal, will allow you that 1 degree tolerance, and the shaft must be in phase. Its inboard yoke gears must lie in exactly the same plane as you see here.